Are we live? Are we live? Hello Internet, we're live. So in this series we will be coding a parser for a language that is a personal project of mine actually, since some years. And the basic structure of that language will be building mathematical theories. So you will be defining axioms and then combine those axioms in all sorts of ways in order to create the theorems. And then this parser would read that language, which is called MathAsm from MathAssembly. The parser will read that language and then output all the axioms and all the theorems that were produced by the file or the files that it would read. And using that language, you can create mathematical theories and proving your own theorems and expanding then that theory further and further and adding more theorems to it. So for the tech stack now, we will be using Kotlin with Spring Boot. And Spring Boot would allow us the flexibility to switch between a CLI application and a web application with a UI very easily. And will also give us, of course, access to its rich ecosystem, like if we want to install Hibernate, for example, or whatever. Spring Boot is a great ecosystem to have. And of course, Kotlin will be used because I think it's a very good improvement over Java, in my personal opinion. If we need a database, we can take an SQL database like H2, which can, of course, then be expanded very easily to a more production-ready solution like Postgres. And if we need a UI, I'm not sure if we'll go that direction, I will use Svelte, probably, even though I'm a React guy and had done some amount of Angular. I really like Svelte. I really like the idea of having a very lightweight compiler instead of a monstrous framework that you should be bundling and shipping to your users. And it's very performant as well. It's more performant than React or Angular. So I think it's really promising. It's not, of course, doesn't have the audience and the community support of React or Angular, but it's growing, it's very promising, and I would like to keep contact with it. So I'm probably going to use Svelte. Okay, now let's go to the actual product itself, to the actual project itself. It's very geeky, so if you're not into mathematics, you can completely skip that section. And if you're into mathematics, so here's my idea on how that will work. So you will be defining axioms like that. This is an axiom. You would write axiom, give it a name, and then say the symbols that it consists from. And you always have this operator that actually separates your axiom in a left part and a right part, a left side and a right side. And what the axiom says is that the symbols on the left side can be replaced by the symbols on the right side. This is a replacement rule, so to say. And the second version is the one-way replacement, which does exactly the same, but you can use it for situations where you want the left part to be replaced by the right, but not the other way around. Because sometimes this should be one way. So you have one-way axioms and two, like unidirectional and bidirectional, you can say, axioms. Okay, and you have something called weight. We will talk about that later. Just hold with me. But you can also define axioms of bidirectional or single directional direction with higher weights. So we'll come to that back. Then, of course, you don't have to write your whole theory in one file. Of course, you will have an import-export system. So you can split your theories in multiple files. And, of course, maintain the volume of a large mathematical theory, like, let's say, Boolean algebra, for example, or arithmetics or whatever. how we're going to import things. We write import, then give it a local name that you want to refer to it locally, and then write its full path on the theory. Imagine that like directories, like Java packages, and then at the end you have the file that creates that thing. And so you have, of course, you can give different name if you want the local name to differ from the original name that it was meant to be. But you can also use the same conventionally. I think for the most cases, this could be the case. And then you can prove theorems by getting some existing statement, axiom or theorem. Statement is an umbrella term for axiom and theorem. Take any existing statement that's already defined above and perform a couple of operations to it, and MathAsm defines exactly what those operations are. There are very few, there are probably 6 or 7 of things that you are allowed to do in a statement and to transform it into a different statement which is going to be your theorem. The way it works, you get an existing statement. So let's say that you want to prove that false is not true, right? And then you have a couple of axioms. You have this one, and then you have, let's call it other axiom, which you would say, for example, x is the same as not x. And I always put space between because, of course, a symbol can consist of multiple characters. So this would be one symbol. The word Boolean would be one symbol. So always put space between different symbols. So we know from the Boolean algebra, for example, if we are trying to build here Boolean algebra, we could say something like x is not x. And then you would have to say that x can be true, like a Boolean can be true. And you can say, for example, like that, x can be replaced by true, not the other way around, of course. And here the way it comes into play, we will talk about it in a while. And of course, also, let's call that Booleans are true, or can be true. And then Booleans can be false. So a Boolean can also be false. And then let's say that we wanted to prove, based on those axioms, that false is not true. So we would do the following. We would, first of all, base our proof on an existing statement. For example, that. So we take axiom 1, let's say theorem, and let's call it false is not true. Then we would take an existing statement like true is not false, for example, and then start performing operations to it. And actually a better start would be that. We start with that, basically. And then we say, we perform the operation replace all, and we write this like that. So we get this axiom here, and we say, we replace all occurrences of x with false. And in that point, of course, we had this. The result will be that. And suddenly, that here. And then if we replace x with false as this axiom dictates, we get false is not false. And then we see how easy it will be. We can replace this with true. So how we can do it? We can say on the right side of this statement, at position, let's make it 0 based. That's position 0, that's position 1. At position 1, I see that you have the statement that the right side of this axiom mentions. So I want you to replace the right side of that with the left side of that, because this axiom dictates that this can be replaced by that. And in order to specify that I want to replace the right side with the left, you say simply invert. Invert. So basically, if you get that axiom, the inverted version of that is you simply switch the right with the left side, and what you get is basically that. Okay, you are allowed to do that in the bidirectional statements. So actually, not false equals true, and then you get that, and you say replace that with that. So here we are, we replace that with true. Sorry, here I forgot that. And then it's the end of proof. It's exactly what we wanted to prove, that false is not true. So we started with this, we took this axiom as a base, and then we used that axiom and that axiom, so we combined 3 axioms and we built a theorem. And this theorem, like our parser, would read that language and would be able to output us this result. That now you have a theorem that you call it, it's called false is not true, and it has that value. So we will write a parser that does exactly that. Okay, that's the mathematical part. We will, of course, define the I think it's seven operations that you are allowed to do, 7 ways with which you can combine existing statements to produce new statements, aka theorems. And we will be defining that as the series progresses, and we will be coding that. We will be giving it bone and flesh and make an application that executes that. So that's the plan of in this series. Okay, let's start then. Create a project. Let's go to Spring Initializer. It's the way we can start a Spring project. Kotlin, please. Gradle. Of course, Gradle. What was that question? Okay. Let's choose a package. MathAsm. Let's call it MathAsm new. I have already projects, by the way, called MathAsm, and I plan to remake it from scratch, but I have to give it a unique name. Let's call it MathAsm new, or MathAsm 2 actually. Let's call it MathAsm 2. Okay. Description. Spring Boot project implementing MathAsm language. MathAsm. The MathAsm language. Okay. Package name. No. Okay. I wanted that to be the package name actually. Yes, that's the package name. jar, Java 18, yes. And dependencies. Okay, what dependencies do we need? Do we have the test already? I think the test is included. No, okay, no dependencies. I will not start with Spring Web. I will not put anything. I want to start really from scratch. I'm not sure if we will build a CLI application or a web application or both. But it's, of course, always... they had now to move. It's always possible to do it after, so it's no problem. Let's generate this. And let's save it to... yeah. Let's save it here. And then let's open a workspace and it was Kotlin, yes, and here you are, MathAsm to zip, yes, extract here, and now we need to open that. Of course, we will open it with IntelliJ. What else? Yeah, we don't need that anymore. No, we don't need to open that project. Cancel. Nice. And we need to open. No, not job. Yeah, but the directory name is stupid. Why did they put an empty space here? Anyway, whatever. I have to change that. No, sorry, I have to change that. That is a very bad start. So, Kotlin, here. Yes, MathAsm 2. Yes, better. Much better. Let's open IntelliJ again. And I think we have a project. Yes, so open. Home, yes, P, yes, Kotlin, yes, this one we need. Good. Finally found it. So, okay, let's see what we have. Of course, we have the, yeah, why it's called like that now? Because of stupid XML files of IntelliJ. No. Okay, maybe Spring Initializer really created a directory like that. Like, okay, we need all of that in the top level, please. We don't need a directory like that. Thank you. You go to hell. And root project, okay. Let's see the build Gradle. Okay, what did this guy injected here? Okay, Spring Boot, yeah, we need that. Yes, the Kotlin things. Okay, seems legit. Seems legit, good. Now let's see the source code. We get a main and a test, of course. Why didn't open Gradle yet? Okay. I think IntelliJ does not understand that this is a Gradle project. Just... Don't you have link Gradle project? Yes, trust project. Yes, okay, now it got it. Nice. So, install your dependencies. Okay, it's already doing it, great. And then Gradle v, and then put run. This should do the trick, but we have to wait a little bit until it builds. So until that happens, I will need to leave you for 1 minute, and until I return, you can hear some music. I'm right back. Okay, enough of that. Well, let's see what it did. Oh, it's still doing things. Oh god. Downloading Gradle 7. Okay, I've never used Gradle 7 yet. That's gonna be interesting. By the way, what did they change in Gradle 7? Change log, or migration guide, or whatever. Release notes. Upgrade instructions. What the hell is that? Ah, it's how to upgrade. Okay, no, I don't care about that. I care what is new. Performance improvements, yeah, new features and usability improvements. What new features do you have? Native support for Apple Silicon. Oh god. Support Java 16. Okay, that's good. Centralized dependency versions. There are a number of ways to share dependency versions between projects and multi-project builds. Multi-project builds. Okay. Yeah. Groovy 3. We don't use Groovy. Who's using Groovy? Plugin development improvements. Build reliability improvements. Dependency management improvements. What did you change? Plugin management. Plugins. API version attribute. Gradle versions. Ah, okay, you can say that. Okay, they are doing that for their own backwards compatibility, I guess. Okay, did you finish? Not yet. Okay, indexing Java 14. No, it finished. Let's see. Good run. It's doing things, compiling. Good. It's building. And if we would like to create a Gradle build without tests, build you. Oh God. Sometimes I'm disappointed of myself. Okay, so build. It built a jar. Tell me it built a jar. It built a jar. Yeah, okay, it's working, guys. It's working. So let's write this on README. Let's go to help. I don't need help, I need the README. Where's the README? They don't have README, my god. Okay, new file, readme.md, and I will write about the project. This is one, and then run with Gradle the put run and build a jar for production with, of course, we have the tests, run tests with it's Gradle the test, and let's be good boys and put that into code. Yes, good. About the project, I will copy paste the notes I have in this YouTube video. So where do I have them? Intro, I just copy paste that. That actually, and more than enough. It's okay. Nice. And actually I would put that at the end, or no, leave it here. Perfect, we have a README. Let's see if the tests are running. Gradle the test. You should be running the test, so nice, it's running. Okay, let's see the code. What do we have? So compact middle packages, please. No? Good. Thank you. So it's called like that. Okay, fair enough. MathAsm 2 application test. Okay, context loads. Let's see if IntelliJ can also do that. Perfect. I just want to make sure that IntelliJ is using Gradle under the hood and not its own build and run using Gradle. Great. Great. It's important. Okay, nice. So now let's start with the difficult part. What we have here in the code, we have just the application, does nothing yet. Okay, so let's see what we need to build. We need to build a parser that can read that stuff and do something with it. So we will definitely need like the module of the system that I can imagine will be parser. It's gonna read literally the characters, character by character, and be able to output something out of them. So that's one module of the system. Then the actual teeny tiny rules of how you combine existing statements and transform them to produce new statements is gonna be the core actually of the application. Let's call it math. I'm not sure how to call it. It's actually, let's call it math because it's the way you build mathematical theorems. Let's call it proof actually because you are proving theorems. Let's call it proof. So you're building a proof. And I think these two are gonna be the two main modules of the system. I will probably start with that one. I will probably start with the mechanics of parsing. It's probably the most boring part, but we need that to have some solid base in order to start actually doing things, writing theorems and extracting the output out of them. So the parser will be of course essential. And then the teeny tiny rules of the proof, we're gonna also have to implement that very, very soon. Okay, so let's imagine how a parser would look like. First of all, let's make a package, call it parser, and another package that call it proof. And let's focus on the parser. Let's think of how a parser would look like. Let's create an interface and say MathAsm parser. How would the data model look like? First of all, you probably need the function parse. The question is what we return. We will see that. Let's say, let's call that MathAsm parse result. Let's call it that way, and we will see what it will go there. Let's say val name string whatever. Just put something here. We will see what will go there. So we return one of those guys. I think makes sense. And what we want to extract out of a file would be the exported axioms and theorems actually. So we need something like a list of exported items, and then list of MathAsm exported item. In essence, this would be a statement. Like item is too generic, maybe statement is too more specific, because the only thing that we export are statements. It's axioms and theorems. That's all the things we export. So statement, let's call it a simply exported statement. So this will be, of course I will put all of those in their own files. I will not create a file with all of them inside. I'm just doing it temporary so we can see them all together. So it's gonna be data class exported statement, and again what a statement is made of. Left side it's a list of strings, and then the right side, it's again the list of strings, which means basically which symbols I have on my right, which symbols I have on my left. And then whether it's unidirectional or bidirectional is also important. So let's call it is bidirectional. That's a boolean. We need a name, of course, well, name, symbol name. Like, it's exported as some axiom, as my theorem, so we need a symbol name. We also need to know if it's a theorem or an axiom. So let's say is axiom boolean, even though probably an enumeration would be better for that case. Because what if we have some third type of item in the future? Okay, let's start with a boolean and maybe we will expand this to enumeration later if we need to. The other thing we need to know about each exported item, it's the weight. Basically, if you don't write a weight like here, the weight is 0. And if you write a weight, you define it like that. I'm not 100% sure about the syntax, by the way. I think I will keep that one. Let's see. So if you define a weight, then you have to specify. It's an integer number, by the way. It is a positive integer. So we need to know the weight. Yes, int. And so the parser, when it parses the file, it returns us a list of exported items. Or let's call it statements. So, what the parser takes as an input to do that. Okay, we need the reader first. We need an interface that would really give us the characters, character by character. This is gonna be our tool to work with. So, reader or input. Let's call it input. Input. It's reader. Yes, Java. I think this interface is general enough, right? It has the read, which is an int, I think. Read, yes, int. And it doesn't throw an exception. It returns -1 at the end. That's good. That's good. Makes things easier. So we need a reader. What else do we need? Like, imagine now we're implementing this thing. We will be reading. Here we will construct an axiom object. That's fine. We will see what's on the left, what's on the right. If it's bidirectional or not, the name. We can construct that. And then, okay. At some point we will need import statements. Import statements, we will need to resolve that symbol. To say, hey, environment or whatever I have around me, give me that symbol, resolve the symbol for me. So we need a symbol resolver. MathAsm symbol. No, let's not call everything MathAsm. My God, that's a bad habit. Let's call it symbol resolver. And now what a symbol resolver is. Okay, that's the result. What we return. And we will make an order after. I will put everything in their own files. We will make nice packages, everything. But for now, inputs. So we need inputs. Interface, symbol resolver. Let's see what we need from symbol resolver. We would need to say, hey, please give me that. So we will have a resolve method which takes the name of the symbol and then gives a resolved or an imported statement. Again, because what are we going to import? Imported statement. Okay, if it doesn't find it, it's going to throw, I guess, because hey, if you write a non-existing thing and the compiler, it's not the compiler, but the parser sees that, of course, this would be an error. So I'm not going to return nullables here. Let's see what this would look like. So when you resolve a symbol by its name, what you need to know about this symbol? First of all, is it a statement, or is it like, can you import that simply to have a shortcut like axioms is Boolean axioms, and then you can write, for example, axioms.foo. Maybe you also need to import, let's call them containers that contain inside statements. Okay, in that case, that's tricky because we need two implementations, then this would be an interface. Or have a Boolean flag. Let's make a Boolean flag is container. That's a little bit dirty. We will see, maybe we will make it better afterwards. And then from an imported symbol, you know what? I don't want to make this decision yet. This is too immature. Let's leave import statements for later. I'm not sure how I want to implement them yet. Because I want to make possible that you import things like that to create shortcuts, and also import statements. And this thing we can call it, it's like a package for Java. Think of it like package simply. We can call it container that contains inside it other containers, and at the end it contains statements like axioms and theorems. And I want to make this possible. So the exact implementation would be a little bit complicated. Let's leave it for now. We don't need it for now. When we reach the point that we need import statements, then we will probably do a good job and do it. So the final thing that the parser will need is the mathematical calculator that does the actual calculating. Comes here, replaces things, finds, replaces all that rules. This will be probably injected by that module here. Let's call it the one who implements the rules of MathAsm. How it would be a good name for that? Names are the worst part in programming. My God. So it's the proof executor. Let's call it the one who executes the proof. Let's call it that way. Maybe not perfect name, but good enough. So interface proof executor. What does this do? It accepts a statement and performs the operation to produce another statement. So it produces the add operation, it does that, it does that, it does that, it does all the necessary operations to lead to the final result. Okay, so we would need the rules of MathAsm is definitely clone right. Clone left side. It's how we start a theorem, basically. We start a theorem by either cloning an existing statement, cloning its left part, in which case we would start from true is true, something like that. So we just clone the left side. We can clone the right side of an existing statement and start with this as a base. We basically get a tautology, like these symbols equal themselves in a sense. Or clone the whole thing and say I start with the whole as a basis. Like I get an existing statement and based on that I build a new statement. So we have clone right side off, clone left side off, and then clone the complete thing. So we have 3 clonings. And then we have an replace all. It means all the occurrences of this symbol will be replaced by that symbol. Like you remember, we had this expression and this statement actually, it's not an expression, it's a statement, and we replaced x with false. So this became false and this became false. This is a replace all operation. And then we have replace left, replace right. It means replace all but only in that side, or replace all but only in that side. And then we have single replacements. Replace one, replace a single, let's call it, replace single on the right side, and replace single on the left side. These are the only, it's 8 operations that MathAsm provides. With these 8 operations, the idea is that you can take any set of axioms and prove any theorem. That's at least the basic idea of MathAsm. I'm still not 100% sure whether those rules are sufficient to build, existing mathematical theories or not. But I think they're a very good start. If we find out that a rule is too flexible and allow for too much, so it produces contradictions basically in a mathematical sense. It allows for falsities to occur, or if it's too restrictive and we need, another operation that will allow for more flexibility, we will see that as time progresses. But I could build substantial amount of Boolean algebra and arithmetics by those 8 operations. So they look kind of universal. We will see. So we need that executes the things, and then our parser would say, hey, executor, do that. Do the actual business logic. Perform that. And then our parser would collect the result and simply export it in the exported exported statements here. So okay, to clone the right side off, we need an existing statement, which is gonna be statement, and then we will have a MathAsm statement. And then of course the left side of that, and again this MathAsm statement would live in the proof module. Actually the proof executor also, this should be on that module. Let's put it that. Let's start creating that actually. Let's create a Kotlin file, proof executor. So we have that here, and then MathAsm statement would be also an interface which represents a statement. What a statement has, it has left part, it's a list of strings basically, get left, get right, again list string, then is by directional, so it's a boolean, get weight, it's an int, and what else do we need to know about that? I guess nothing, that's all, I suppose. Yeah, so we have that, and we say clone right side of that, which will produce a new MathAsm statement. Clone left side of that will produce a new statement. Of course, a cloning produces something, and that produces something. All the operations produce something. They give you something, and then this is why it works like chaining. you get the result of that, you feed it to the next, and you get the result of that and feed it to the next, and so on. And we have another one. Sorry, it's the invert. Invert. You get an existing statement and you invert it. You remember we inverted that one in the example below. Here it is. We invert it and we say then replace actually the right with the left and not the left with the right. So we need to invert, and then we replace all, and then replace left, and then replace right. For the replace single on the right, we need the position. It's 0 based. Generally, I hate writing comments, but here it makes sense. I think we should type that position is 0 based index. In both of them actually, but I think one is enough. We could name it, of course. We could make the code say that 0 based index. You know what, maybe that's even better. Yeah, comments are useless. Like, make the code speak for itself. Yeah, it's not useless. Sometimes they're useful, but 99% making the code say what it means is better, I think. Personal opinion. Nice. Okay, so we have the proof executor. Let's import that guy. And then our parser, with the help of a reader and a proof executor, it will be able to produce these concrete results. So let's put that in its own file. So yes, here, refactor, please put it in its own file. Thank you. And you also in your own file. And then the whole challenge would be to write an implementation of that guy. An implementation of that guy that this module would be exporting then to the outside world. So it's going to be a CLI or a web application or whatever it's going to be. Okay. Deep breath now and let's start implementing this guy. Okay, so to implement this guy, we write a test that fails because we will be trying to practice TDD. Not sure if I will be disciplined enough to do that, but that's what good boys should do. So let's try that. We write a test that basically writes MathAsm parser implementation. Let's call it that way. You know, that's not a meaningful name, but I cannot think of anything more. Just want to hide this behind the interface for respecting the dependency inversion, how we call it, principle. So this is the test of that class. So it's internal. Yes, thank you. And let's write that test. Okay, let's write an easy one. Empty MathAsm file should return empty result. Makes sense, right? Hopefully. So how we would test that? We would say, okay, let's create a private val. Parser is MathAsm parser implementation, which does not exist yet, and that's why the test fails, which is the whole concept of the TDD. So we create a parser. We need to feed it a reader, actually. If we feed it a reader, it makes sense that we initialize it in the test. So and then we write an empty string to reader. Gifts. Does this exist? To reader. Let's see. Kotlin string to reader. Reader from string. How you create a reader from a string? String reader. Really? Reader. Yes. Okay. Great. I love Kotlin. So we create a string reader, and then we need to create where are you? Proof. We need to create a proof executor to feed it into our parser. .parse. Yes. So we need to mock it, because that's not the concept of that test. So private val executor is mock k. Tell me that you have mock k. Okay, import. You don't have mock k. No, that's bad. We need to. Okay, let's write here test dependencies. So we need an assert j. Of course we need assert j. Okay, let's make some serious work here. Assert j Gradle. We need to write nice unit tests, and the way to do that is, but I will not take it from that page. Assert j core. Yes, this is the one. What's the latest version? 3.22. When it was okay, it's cutting edge. Okay, let's take that one. And if it doesn't work, yeah, of course, in production I would never just get the latest version of something like that. But here we don't care. Let's take the latest. And then we need mock k. Yes, mock k. Let's also take the latest test implementation. Yeah. Please install that. So mock k is a library for mocking, and assert j is a library for writing assertions, which in my opinion are much more elegant than the ones from JUnit, so I just use it. Okay, so we have a mock. We don't have that yet. And okay, actually, you know what? We can write this here finally. Private val, and then let's write parser. It is a parser implementation, and then we need to write simply val result is parser dot parse the string and an empty string and with a mocked executor, and the result which we are going to take is assert that, come on, import it, yes, this one, result dot is empty. Okay, of course now nothing compiles, because the point of the TTD is to write a test that fails, but this test should very soon pass. By the way, let's create a Git repository. My God, how did we forget that? Git init. Thank you, Git. And do we have a git ignore? No. Okay, touch git ignore. I think we write it this way. Okay. Yes, please. Where's the git ignore? Here. Ah, it has a git ignore. It has a git ignore. So what did you do? Okay. Yeah, that's out. Git status. Let's see what we have. Git ignore, readme, build Gradle. No, that's not all. You still have the source files. Where are those? Ah, okay. Nice. Nice. Git go. Git. Okay, let's do this from IntelliJ because it has all these beautiful code formatting, and I'm lazy to do that explicitly in every file. So initial commit then. What errors on what coordinates? Yes, I know my unit test does not compile. That's the point. And upgrade. What version of Spring would we have? Yeah, we already have that version, don't we? I don't really understand what version do we use. Okay, in any case, let's ensure that we get the right ones. Spring Boot version. Spring Boot version, yes, please, Gradle, do your Gradle things. And now we are sure we have the latest Spring version. Okay, in the meantime, yeah, please commit that. Yes, commit anyway, we don't care. And let's create a Git repository for our new project. So let's go to GitHub and yes, and create new repository. Let's call it MathAsm 2. And let's say a parser for the MathAsm language. Yeah, it's public. No, we don't have a license. Okay, we need to pick up a license. We will. Yeah, git init, I did that. Yes, we did that. Please give me a break with your main bullshit. So, yes, git boot source master. Please, I cannot stand this shit. Master. Okay. Yes. Okay. Yes, I should just. Yes, this is what I did actually. Do I have this? Okay, git push. Everything up to date. How so? Oh, we're live. Nice. Okay, everything up to date. Great. We are in Git. So now, let's create the class, of course. Of course, in the production package. So now we have to write code to make this test green and happy. And this is what we're going to do right now. So let's go to parser, create the file called parser implementation. You are a MathAsm parser, which is your whole purpose of existence. What? Yeah, you're missing the members. Yes, exactly. Return MathAsm result, empty list. Maybe it's a function. Wait a minute. Result.export.statements is empty. Yes. Assert that the result. So now we have our first test that hopefully will pass. Beautiful. Now, at the moment I will be pushing to master directly. Once we have some basic stability, I will start using branching, but at the moment we are in the baby steps of our project, so I don't think it makes sense really to start doing it from now. I will change this name, it annoys me. To yes. Yes, I don't see what you mean, but probably yes. Yes, definitely yes. You were right. Let's see if the Gradle picked our rename up. No, we don't have main class actually. Yeah, we will need to then create the jar file and so on to be production ready to say what is our main class. But at the moment I think it's gonna work. Let's see. Put run Would that work? Yeah, it's working. Test. It's executing. Good. We are all good. Okay, let's close the noise and start actually implementing something. So, we should support comments. Let's start from comments. It's probably the easiest thing. So, double slash, or should we use the hash notation for comments? I'm not sure. Let's use double slash. I'm too JavaScript guy. So, double slash means a comments, and basically the parser should ignore everything until the end of the line. Basically. So let's start implementing that. And file with only a comment should return empty result. And maybe we'll have multi-line comments. So let's say a single line comment should return empty result. So our input will be simply a string and say this is a comment, and our parser should see that and simply do nothing because it's just a comment, and we should get an empty result, which would already work. Nice. Let's write more tests. Let's support multi-line comments. And again, multi-line comment should return the result. All of those tests should pass. So if we read empty, we get empty. If we read simply a comment, we get empty. If we read a single multi-line comment, we get empty. And this is where the easy stops and the difficult starts. So let's commit that and say set up basic tests. You know, this kind of becomes repetitive. Let's create an util function for that. Let's say parse string input string, and then it returns a result, and then return exactly that thing, where here you have simply the input. This is referring to this dot, of course, and then we save ourselves this repetitive part here. Let's do that. I like this sometimes, maybe habit from JavaScript, maybe because Kotlin has ambiguity of the this sometimes, and this can cause surprises. So maybe I'm a bit paranoid, but I like doing that. So let's keep it for now. Nice. And now we will start trying to parse our first action. File with one axiom should return a result containing one action. Sounds pretty reasonable to me. So one action would be something like, according to MathAsm syntax, you know what, let's exactly try to parse this one. And yes, this should be escaped because Kotlin. And then we would have has size 1. We expect one statement here. And then let's say axiom is first. So we need to assert that axiom is true, of course. Assert that. So if we create an axiom, we should of course get an axiom. What else do we need? The name. Of course, the parser should return the correct name. Is equal to, we expect to be some axiom. And then the left side, the right side. Or you know what? We will write separate tests for that. We just would like to see that the list has one axiom, nothing more. Has one and it's an axiom. So of course this test will fail now. And this is exactly where we should write some real code. So the fun is over, now the serious shit begins. Yeah, we will write a lot of code to make this pass. So this is gonna be the point where our happy unit testing path ends. Of course we could test simpler things, but it's gonna be really cheating. Like at some point we have to really dive into the parsing things, digesting characters, splitting them into tokens, understanding the tokens into syntax trees. We have to do that things now. It's gonna be fun, and definitely not going to end in this episode. This is gonna take us 2 or 3 episodes to finish, I believe, to completely finish. But then we will have a parser. Hey, that's gonna be the good news. So I will commit with the same message. I'm not creative at the moment. Let's push everything and let's make sure that it's get pushed, and yes, here we are. So the parser should have internally scanner. It's a scanner actually, a tokenizer. Let's call it tokenizer. And the tokenizer gets the input and starts giving you the next token. And we will say get token. Next token, or simply next. I think that's better. And we will get a token. Let's call it MathAsm token. And what is a MathAsm token? Can be anything. Can be keyword, action keyword, identifier, equal sign. Probably this is one token. I'm not sure. No, it's not one token. String open. It's one token. Every meaningful symbol of the language. So this is a token. This is a token. This is a token. This is a token. A new line is a token. This is a token. This is the token. So we need to get the next token. We also need to skip until end of line. and maybe return the next token that you found after the end of line. So this would be useful for single line comments. Let's imagine that we see this token, and then we see this token, and then we understand, hey, we are parsing a single line comment. We just should skip all of that and return the new line, basically. So skip until multi-line comment end. So imagine that we have a multi-line comment like that. We should skip and skip and skip no matter what we encounter until we find this, and then return the next comment, even though the next comment would always be star and slash. So I'm not sure if this makes sense actually, and this would always be new line, so it's pretty trivial. Yes, so we need to implement those three things. We will need them. We will definitely need those things. And the next token should of course keep all the white spaces before. And now the question is what a MathAsm token is. And the fact that can be anything from keyword to empty string to symbol means we have to make it a sealed class probably. So MathAsm token, and then we have actually I don't remember the syntax very good. I don't use inheritance like that often, to be honest, but in this case it's a pretty good one. So you can do it like that. Okay, we can do it in interface. And what's the difference between sealed class? Okay, sealed classes can also have fields on their own. No, we need an interface. We need an interface actually, so sealed interface. And then we have inside it, we don't even have to do that. We write class end of line implements MathAsm token. So, hello, what? Sealed subclass has no state and no override equals. Okay, we need to have state. Maybe data class? No, of course not. So what do you suggest, dear IntelliJ? We can do it object, of course, like why not? Okay, so end of line, we have the end of file, we have axiom keyword, we have slash actually for comments, we have the star, or you know what, we could consider this one token, so let's call it comment start. We mean simple comment start, and then we say multi-line comment start, multi-line comment end. What else can we have? I'm not sure, to be honest, if we even need that. Probably the parser should completely skip that and return you the next meaningful token. Probably this would be better, and not to have to deal with token comments at all, but we will see. The implementation will show us. We have this keyword, we already said it, identifier. So an object like a name, symbol identifier, and this needs a name. and this is a class. So what else do we have? Let's say class axiom start. It's basically a string. That's an object. Doesn't have state. MathAsm token. Then axiom end, and then axiom symbol. That's a class, by the way. It has text. It's basically we have this symbol, and 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 so on. So we need to know the text of the symbol. And then we have the bidirectional separator and the single directional separator. It's a little bit much, but they're not going to be that many. At some point we will reach the end, and that's going to be all of our tokens. So bidirectional bidirectional, I think it's one word, bidirectional separator, and then we have the unidirectional separator. What's the problem? It's never used. Okay, we don't need a class for that, those are objects. Nice. What else do we have? We will support import statements later, so for the moment it's okay. We have the theorem keyword. So axiom keyword, we have the theorem keyword. Nice. That's an identifier. That's an equal. The equal sign. We forgot about that. Equals. Have an equals. And then we have identifier. This would be identifier. This would be a dot operator. We need dot. We need comma. We need parenthesis open. We need parenthesis close. We need numbers. Value. Let's call it value. It's an int. It's a class. What else do we need? This is not part of the syntax. So, yeah, you know what? This simple comment start, multiplying comment start, just forget them. Like the parser should give us the next non-comment token. We shouldn't have to even consider tokens at all when we're parsing. Tokens are simply ignored. So these are going to be internal details. We don't have to have them in the API. The API has only the next. Just give me the next, give me the next, give me the next every time. End of file is considered a token, of course, and end of line considered a token. So, do we need anything else from here? We have the private keyword. We have one more keyword. Private keyword. Okay, control characters, keywords, support characters go here. Number, token, and identifier go here, kind of like value things, and then axiom start, axiom end, which are basically the same symbol, but let's keep it that way. or yes, let's say quote, simply one thing, it's simply the quote. And then we have these opening closing things, so quote, parenthesis open, parenthesis close, and we also have bracket open and bracket close. And then we have axiom symbol, and then we have the two separators, unidirectional and bidirectional. What's the problem here? Save, delete, rename, typo. Unidirectional separator. What did I write? I forgot the I. My god, I forgot an I. Okay. So let's put those guys in another file, and let's call them. Actually, let's create a directory and call it. Let's call it internal, because it's gonna be the things that we're not going to export to the outside world. Like the outside world will not care. Also, that will be in the internal, probably. Yes. Anyway, and then we have here token, everything that has to do with the tokenizer, and then we call it MathAsm token, right? And then we define our shield class, shield interface here. So we import that guy. And then the tokenizer should also be here, parser internal tokenizer. Yes. Yes, and then we have our tokenizer, our token here, okay, and our tokenizer here, which should return, okay, let's return now end of file. Nice. And our parser now, which should also be in the internal but not in the token, right? Just like here. And also our unit test hopefully also, god, sometimes IntelliJ is stupid. So parser, create new package, internal dot token, and you go, not in the token, sorry, just in the internal, not in the token. But we can test the tokenizer as well, so it's fine. We will be definitely unit testing the tokenizer, like obviously. So okay, we can close the tests. Now let's go to the tokenizer and create a test. It's not private. It's not private at all. Create test. Yes, create test. And here actually we should also nice. So now we need private val tokenizer, or not, because we need the stream each time. So let's just create a test function should return end of file for empty input. Sounds reasonable to me. So we have tokenizer, and then you know what, let's create simply an extension function, like a, okay, let's say private fun tokenizer dot from string. Let's call it input, and we return a tokenizer. Yeah. But that's gonna be that's not gonna be static. God. Or let's call it simply create tokenizer. Easier. And we return that. So we create a tokenizer from empty string, and then we expect assert that yes, no, just import it. Nice. Tokenizer dot next is equal to end of file. Let's see. Let's play that. It is great. So now we have to actually start reading our input. So let's see. So let's say val next char is this dot input read. And then we can say if next char is not -1, which would mean end of file. Actually, let's create a constant for that. Private const val end of file is -1. So and then we have the next, that's the next int actually, not even next char. And if it is, then return actually end of file. Else we have to do something to return something meaningful. Let's at the moment return that everything is, let's pretend that everything is an identifier. So let's return an identifier with the next int as char to string. So we create a char code and then we get to string. So of course it's not correct, but we will be able to run some tests on it. Okay, so should read identifier. So hello, the next token. Okay, let's get first, let's say token, and then let's call the dot next function, and we will say that assert that token is instance of symbol identifier. And then, or you know what, let's do it that way. So this will throw an exception if it's not, so the test will fail. And then we say assert that token dot name is equal to hello. This should do the trick. And then the next thing that we should read would be an end of file. Assert that, yeah, we need the tokenizer for this. Yeah, we need the tokenizer for this. Okay, so tokenizer dot next. We need a variable for that. Val id token is that as symbol identifier, and then this symbol identifier should have name equal to hello, and then the next that we would read should be the end of file. This would probably work with one letter, with one digit. Let's see if that works. I think we should at least be able to parse. Oh, we parse this. Nice. But as soon as we will try to parse 2 characters, then we will probably fail because we don't have the code for that. Sorry, hi. I would like to spell hello, but hi is better. So this should fail probably. Yeah, we don't have, we just parse one letter and we return. So the first question we should ask ourselves is that if the character that we see is really identifier start, like we start reading a letter. So if it's a letter, then we know we start reading an identifier. So let's go and say if is identifier start next int. Actually, we need this as char. Working with ints will be a little bit stupid. So let's say val char. Maybe let's create a function, say read char. Create extension. No, here. Yeah, reader, but here, yes. So let's create an extension function and say you return a char optional, and then we can write that. Yeah, we can extract the return outside. Actually, we can write even in one line because it's going to be very short. Next into char. That's actually the next char function. And we can write here read char else return end of file. This is, I think, a little bit more elegant. So we'd have the next char, not the next int. That will make things easier. So let's remove that nonsense and start writing something more substantial. So we don't need an extension function now. I don't understand why. Tokenizer, yes. So it is an identifier. Return if char dot is, oh, it's Java identifier start. But you know what? I don't want to couple myself to the rules of Java. Let's say is letter. Return char is letter. So if it's a letter, then it's an identifier start. We can make other exceptions as well, like allow underscore, something like that. But for the time being, that's gonna be enough. So if it's an identifier, then we need to take that and read the whole identifier until its last character. So let's say if it's an identifier, this dot read identifier. The problem is we already read one character of the identifier. So imagine that the identifier is this. We read the n, we know that it's an identifier, beautiful, and then we need to read the next, all of the next. We have two ways to do that, because of course we will lose one character, then we will lose the first one. We have to pass the first one explicitly and say, hey, by the way, I already read one character, it was an n, So consider this when you build the identifier. That's one way to do it. The other way to do it is to roll back one character before. Say, hey, okay, I know it's an n, I know it's an identifier, let's go one step back. And then read the whole thing. This is the second approach. I think this is a little bit more promising approach to enable a rollback functionality. So, okay, first of all, let's call it next char, and I will not do it an extension function actually, because it's gonna be a little bit more than that. We will have private fun rollback character, so we will be able to roll back, but we will be able to roll back only one at a time. So we will have a private variable here. Unfortunately, it has to be stateful. I think a small amount of private state is okay for dirty little low-level work like that. I don't think we can really avoid it. So rolled back character. So now, if this is not null, then we should throw. Let's create an exception. Illegal rollback, actually private, make it private, rollback exception, and it is a runtime exception. Rollback. So it has to be null, and when it is null, this dot rollback character is the char. Now, each time we read a new char, we will check if we have a rollback character. Okay, let's create a variable for that. Val rolled back is this rollback character. And we say dot if dot let actually. So if it's not null, no, let's make it a good way. So rollback character, let's make it, if this is null, then do that, the thing we did before. If it's not null, make it null and return the thing that you found just now. So this is a complete rollback mechanism, I think. I don't want to remove the, no, I don't want this because it's mutating things. Mutating things is not part of the return statement, you idiot. No, disable inspection. I appreciate your feature, but here is not the place for it. Like, you mutate stuff inside an return statement. What is that? Yeah, that should be it. So when we find that it's an identifier, we roll it back. We roll it back. And then we read the identifier. And then identifier can be also a keyword because these are also, you know, letters. So you cannot really distinguish between those two yet. So we can say this key create keyword or identifier. and we will get the ID. Nice. So now we have to implement this function and this function. We're not that bad. So return end of file. So if anything else, we will not support anything other than end of file identifier at the moment, and then we will support, of course, all tokens step by step. So read identifier, it's a MathAsm token, of course. No, it's a string. It's a string. It returns a string, of course. So let's make a string builder. Our builder is string builder, and then while okay, let's say while true. Well, next char is this next char, and if that's null, we continue or break. So if next char is identifier continuation, actually those things, those char utils could be their own class, because I don't want our tokenizer to be dealing with this. Okay, let's create here class. Let's make it an object, simply char utils, and this thing, for example. We can even make it extension functions like char dot. It is still an util, but and we will put that in another file. So let's put it here. Char utils. Nice. It starts. Our project starts taking a little bit of shape. So we have some char utils, and we have the isIdentifier start. We have the thing that we wrote now, isIdentifier continuation, and we can actually write it this way. Create extension function on char, yes, and please put it here. Return. We will still use the same rule, but in the future maybe, for example, identifier can also be number. Oh yeah, it can also be number. Is digit. So numbers and digits should be allowed to be part of the identifier, but identifier should not start with a number, because then we know, hey, we're parsing a number then. Nice. So let's go back to the tokenizer and say, as long as you are an identifier continuation, put it into the builder. What's your problem? Okay. Else break. So as soon as you find that we stuck to a symbol that was not an identifier, roll it back, actually. Roll back char. Next char. So that then the guy who called you reads the token that is following after, and break. And then return builder dot to string. I think this should do the trick. Yes, and now we call it isIdentifier start. We do it that way. And then we have this function. That's easy. Let's say value. And then we will simply separate the keywords, and we will write return when. Here, for example, I like the return when because it's purely return statement. So if the value, when value actually is axiom, then return axiom keyword. When it's theorem, then theorem keyword. What other keyword we have? Private, then it's the private keyword. Do we have other keywords? No, those three. That's all. Great. Default, else sets. Symbol identifier of value. Now we should be able, I guess, to run our tests again. Probably now it should work. Actually, all of them should work now. Yeah, that's working. Seems good. Seems good. Let's commit. Let's say support identifier parsing. We do something. Okay, we parse identifiers. That's a start. So we can just read things like that. We don't handle white spaces yet, which is a problem. So let's write a test. Try to challenge our little tokenizer a little bit more. Should skip white spaces. So if we start in this state and we have a bunch of white, like should skip one white space. Let's be very specific. So it should skip the white space and it should still say hi and then end of file. End of file cannot be class cast. Yes, of course. So here we get a class cast exception and we should. Actually, can I do instead of, wait a minute. Let's do that. Maybe we have a cleaner way to do that, and that to say that the tokenizer.next is equal to symbol identifier value h. Yes, because it compares, it's a symbol identifier. Yeah, of course, because I should remove that. I'm stupid. Okay. It takes two different instances, but then we should make a data class. Yeah, actually, make all the classes data classes, because they get meaningful equals and hash code. So now it should call the equals. And to be a little bit more elegant, we can create an extension function of that. And let's put it actually, let's create another directory, call it test utils, and put it inside and say parser, and write parser assertions. Nice. And then we create can we extract this, please? No, it cannot. This. Okay, this is an object assert. My God, this will look a little bit ugly, but what can we do? So fun assert symbol assert identifier value string, and then let's say this dot assert equals no, assert that dot is equal to, sorry, is equal to, of course, is equal to a symbol identifier of value. So, and then we can simply say assert identifier. It reads a little bit easier, I think. That kind of seems cleaner to me. So assert that the next token is an identifier with value h. And we can do the same basically is of and of file. So can I write that? No. Okay, let's see if this would work, because this reads nicer. Okay, assert that next is an identifier, assert the next is an of. It could be even cleaner if we can somehow chain that and say assert that you now have you know what? That's even better. That's even better. We will do the following. Math, what we need? It's a tokenizer, right? Okay, then it's tokenizer assertions. I want to invest a little bit on the quality of our tests. It's not gonna take a long time. I promise we will proceed, but this will create a good basis, I think. So tokenizer dot expect identifier. Assert this dot next. Assert that this dot next dot is equal to yes. That's it. And then expect end of file. Let's not shout. Is equal to end of file. So we can do that. Create tokenizer. Look how nice our test will look like. Create tokenizer and then expect identifier h, and then expect end of file. Yeah, of course, we should return every time to chain that, because chaining is nice and elegant. We should every time return that. So return this and return this. This test looks very nice. I really like it. Okay, so then create tokenizer hi. Look how easy it is to write tests like that. So we would expect hi and then end of file, because this input should produce only that and nothing more. And now we should simply, with a space and hi, we should simply return hi. This would still fail, by the way. We haven't fixed that, but we made our tests very, very beautiful. So let's try to run this. Is it still recording, by the way? Yeah, cool. Nice. Okay, this test fails, and this is where we ended last time. So let's go and try to do that. So we will modify our next char, not modify it, but write another one, right? Private fun get next meaningful character, I want to say, but how can we formulate that? Like exclude white spaces, exclude tokens, just skip everything and give me the next character that I actually care about. That's this function. But how can we name this thing? So get next meaningful character, active character, active char. Okay, let's do that. So it returns again a character or null, and we will say the following. Actually, this seems a little bit chaotic. I don't like this code. And this, of course, but it's low level work. What can you do? I would like this to read nicer. It's low level details. How beautiful can they be? Okay. So next char is this dot next char, or return null if you don't find anything. So now, if you did find anything, we have three cases. Case number one would be to find a white space. Case number two would be you find a comment start, like single line comment or multi-line comment. Case three would be here, I get something that is anything other than comment or white space, which mean meaningful character. So this function could be written like that. When next char is letter, no, we can write it like that, is white space. If it's white space, then actually what we should do, we should continue to the next, get next active char. And can we do recursion here? No, actually not. It's not a good idea. While loop, unfortunately. Today we start with all the dirty work. I hope this will get more interesting, because now we really do low-level stuff. It's inevitable. It's the main point of the language to, write a parser. So parsers are low level. Hey, what can you do? So if you find null, just return null. That is in any case correct. So if it's a white space, then continue. And get the next one, and get the next one, and get the next one. Else if next char is comment start. If it's comment start, then this dot skip comment. And when you skip the comment, go ahead and get the next one, and the next one, and the next one. So we will write, of course, all of that. So we just need to skip the comment, actually. Else return next char. I guess that's all the loop. Is comment start now. Let's write here. Is comment start. It means basically that you are a slash. This is what it means. Sorry, you're a char. If you're slash, it means you're a comment start. So now we have to create a function that skips the comments. Oh my god. Okay, we will do that later. You know what? Skip comment. At the moment, skip comment does nothing. Okay, let's see if it now get next active char. So here we will say get next active char. I need to parse a new instruction, a new token. I have no idea what context am I, but somebody asked me to parse the new token. So what I do is take the next active chart, I skip comments, I skip white spaces, I skip everything, get the next meaningful to me character, and then I ask myself if this is an identifier. I do what I did before. If not, I just return end of file. Let's see if this will make this test succeed now. Let's run all of them. Cool. Seems like we have a success. Support white space, support skipping of white spaces. And actually, I would write should skip multiple white spaces, and let's see if this would do the trick. So space, tab, again space, again tab, another space. So all these should say expect identifier. Let's run this. Yeah, cool. It seems like our parser is working. Look at, oh god, we have already so many lines of code. I wonder how we could make this a little bit more structured and beautiful, but not sure. Maybe we would break down classes and say, hey, the identifier reading is a class and so on, but then we'll have too many classes. Okay, let's keep it for now like that. So now skip comment. Let's try to break that. Okay, say test multiple white spaces. Now, should skip single line comment. Should skip single line comment. Okay. So let's see, we start with a single line comment like that. This is a comment. And then we have a new line, and then we have hello. We should get the hello. So the next thing that we should get from this input should be the hello. The token should be completely ignored by the tokenizer and give us the next meaningful token, and then get end of file. We expect that. Of course, this is not gonna happen. Nice. So we have to program this in order to happen. Skip comment. Okay, so val next char is this dot next char, and now we have two cases. If next char is another slash, then we have slash slash, which means it's a single line comment. Say this dot parse single. Okay, let's make a when statement. Better. Single line comment, right? And if it's a star, then parse multi-line comment, and else throw unexpected character exception. Like, I didn't expect this character. So let's create that class. Actually, don't make it private. Why? We need to unit test that. So unexpected character. You know what, actually? Let's write a message directly. Exception. Nice. Illegal character after slash expected slash slash or yeah, that sounds good. Now let's go here and say while true while next char is next char, if next char, okay, when again next char is end of file, then return end of file. If, on the other hand, it's end of line, then, okay, we can do it like that, I guess. Return next. No, we cannot. Sorry. End of file, end of line, then return end of line. What am I doing, my god? Like, get next character. Character is not tokens. So if it's /n or null, then return it. Then return, actually. You parse the comment. So it's like that. Okay, else continue parsing. But on /n we should also roll back. So the next guy reads the /n. So yeah, so null is simply return. /n is this dot rollback character and return. And anything else is simply continuing the loop. So we can spare this. What is the problem? Oh, cool. So if it's null, return. If it's a new line, roll back and return. In any other case, just continue looping until you find the end. And the multi-line comment we will implement later. At the moment, do nothing. Let's see if this will work. Cool. It's working. Did we break anything else? Let's run all the tests. We didn't. We are good. Good, we make progress. So, should return a of if file contains comment only. So if we do that, we should directly get an end of file, nothing more. Okay, now We will support multi-line comments later, actually. You know what? Let's continue. Let's write a to-do here. I think, yeah, let's do the to-do of Kotlin. Multi-line comments are not supported yet. It's not that I'm lazy to do it. I don't want to bore you to death, because we will still have a lot of low-level details, and it's okay if we leave some for later. Like, let's move to more interesting topics, hopefully soon. Okay, so the tokenizer can now deal with, let's go to the test, can deal with comments, single-line comments, it can deal with identifiers. Let's go to write some other cases. So, else if next char is, or no, here a when statement would be good. So let's get the hard-coded things, and let's get them first, actually. Val as symbol and say this.read to symbol, and then let's give the next char. Let's return it. So if it's a symbol, then return it as a symbol. I guess we can write it this way. It's not very clean. Sometimes these Kotlin tricks do not seem so clean to me. So to symbol, it's a MathAsm token, maybe char. So we are sure it's not null at this point, and we just want to see if it's a symbol. So return when char. Now we have all the symbols, like if it's a dot, then dot, and then we have all the cases, and then else null. So this is gonna be it pretty much. Let's see, equals dot comma, equals dot comma, parenthesis close, parenthesis, let's say the open first, close second. So we have the equals, we have the dot, we have the comma, we have the parenthesis open, we have the parenthesis close, we have the bracket open, we have the bracket close, right? Yes, okay, bracket close. What else do we have? That's not a symbol. Okay, I use the word symbol. I mean operator, actually. To operator. Symbols, we say the identifier. Actually, let's call them simply identifiers. That's better. Yes. Expected identifier. Yeah, okay. So to symbol, let's call it symbol. Now we can call it symbol. There's no confusion now. So identifier, that's a symbol, that's a symbol, that's a symbol, that's a symbol. If it's a quote, 1, 2, 3, 4, 5. That no, that's different story. That's different story. Okay. Nice. So if this is not null, return it. Can you do it like that? If val symbol equals that is not null. No, like that. No, I cannot. Yeah, The alternative would be to write it in 2 lines, like explicitly. Val symbol is that. If symbol it's not null, return symbol. And this thing is encoded into that Kotlin line. I'm not sure what I prefer. This wins in clarity. This is more compact, but a little bit, the read's a little bit ugly. You know what? I will go with the old school way. I will go with that. So we now cover symbols and identifiers. Let's go and try to see that. So should read identifiers and symbols. Let's create something fun. Let's say hi, okay, hello plus world, comma, is dot equals, and then what else we have? Parenthesis open, there, parenthesis close, bracket, 1. Let's do that. So, okay, we expect, the first that we expect is identifier called hello. And then we expect plus, we don't have plus. Do we have plus? No, we don't have plus. We had quote actually. Yeah, let's give a quote. Okay, then expect quote, and let's create that extension function in the not charutils, but here. Expect value. No, it's MathAsm token. Token. So then expect a quote, and then expect an identifier that says world, and then expect a comma, and then expect an identifier that says is, and then expect a dot. Big test, but meaningful. Then expect an equals, and then expect a parenthesis open, and then expect an identifier that says there, and then expect a parenthesis close, and then expect bracket open, and then expect a bracket close, and in between of those expect the word, expect identifier called 1, and then expect an end of file. Really, it's working. Good. That's good. That's nice. Let's run all of them. Okay, now we can handle identifiers. We can handle keywords. Let's test the keywords. Okay. Okay, let's do that. Should recognize keywords, and let's write, okay, axiom, then let's write theorem, and then private, and let's write a dot here, for example. So we expect axiom keyword, and then we expect theorem keyword, and then we expect a dot, and then we expect private private keyword, and then we expect end of file. So that should be the test. Nice. We're not that far. The tokenizer seems to work nice. Okay, the question is now when we are inside the string. Here the syntax is a little bit different because here in this string we allow everything to be written. The only thing that we recognize as special is this symbol, the triple equals, which means bidirectional separator. This one, which means the unidirectional separator, and the end of the string. Everything else is completely ignored. By the way, I don't know, something that I thought about now is that charutils is identifier. No, somewhere we wrote is white space in active char. I'm afraid that if it's exactly new line, because this would count also as a white space, if it's literally a new line, that you should return new line. You should return the next char, actually. Because I think technically new line is a white space, but space char. Okay, doesn't say exactly. So if there is white space, let's see. Is white space? Yes. Is white space? No, but no. Thank you. So we should treat new line as a special character because it changes the command. But it's not really a white space in the meaning that, let's say, you would not be allowed to do that. This white space is not the same like a new line. This should be illegal syntax. This should be legal syntax. But when we parse, sometimes we just need to get the next, and we don't care about empty lines. Sometimes we have to think about that. Okay. So sometimes you want your tokenizer to just give me the next one, like from here, I don't want to care about this new line, this new line, this new line. I just want the next meaningful token. Okay. I think that's enough for today, isn't it? Like, we have a good start. We can parse basic things like this. Thing like our tokenizer seems to work. The next steps would be to enhance our tokenizer and finally go to the parser, which would be our actual goal. So the parser would deal with higher level stuff like a statement. Like I'm parsing a statement. I don't parse simply token. Like we would go to the abstract syntax tree level. And then this thing will start getting a little bit more interesting. So this will be an axiom definition statement. This will be an import statement later. This will be a theorem, theorem declaration statement. All that expression here should be parsed and assigned to that value. And the next step after that would be to start implementing the actual transformations. Like here something should happen. Here something should happen. We should start taking an existing statements and replacing things to produce the new statement. That's going to be our theorem. And here it's going to get more interesting. And when we're done that, we will start parsing whole directories. So have many MathAsm files like that. One will import the other, and we will start building a theory and compiling it all and say, hey, give me all the axioms and all the theorems that you just parsed. And maybe then store it in the database and create a UI for it, and then the project will be over. I guess that's pretty much the plan. Okay, thank you very, very much. Let's close that and see you in the second episode.